Right, the light is on. So what, we discuss a few basic. So we discuss a few basic ideas of Monte Carlo methods. So what I would like today is to start the discussion on extending Monte Carlo methods to dynamical problems in a way that is scalable. So a very good way to introduce the subject is to do it through what's called state space models. So today the lecture actually more or less is going to have less of Monte Carlo approaches. Don't look at your computer, pay attention to the notes. All right, what's the point of coming? You can also, not bother to come and just go home and read the slides. All right? So I'm just saying we're going to do this through state space models that are sort of universal models for practically most dynamical systems in every aspect of engineering and the sciences. So I want to tell you a little bit about the notation, the formalism, what exactly we are looking and etc. So this topic is obviously very important for research. So if you work on dynamical systems, if any of you came to the seminar yesterday, you know that these are universal problems. So these are things that you need to know. Again, today there's going to be less of Monte Carlo. I'm going to try to finish it up, some of the preliminary ideas tomorrow. So I'm going to tell you a little bit about the state space model. I am going to do some setting of the Bayesian inference problem to tell you what exactly we want to compute. And also, I am going to give you lots of recursive equations for estimating the state on these models. These equations can be extremely useful because they can lead to analytical solutions, so you need to know them, but we're not really actually going to use them. We're not going to use at least all of them for Monte Carlo methods, but you need to know about them. Okay. Now I know some, in other universities, on this topic, you may have to take a whole course. So here we will cover it in 30 minutes. Okay, because you guys are very tired of taking courses, and if you could take 0 courses, you would be happy, right? All right, and then. Somehow, if we manage all of these things, maybe tomorrow we will discuss, we will review important sampling, and then we will see how important sampling is applied to this type of problems. The literature is huge, and so if this is a research area, you should hit these links, because not only there are books online, hundreds of review papers, but also there's a lot of video lectures on the web that you can follow. Actually, some of the video lectures are complete courses, right? I mean, I see here, my eyes go to this, the Doucet's notes on sequential Monte Carlo methods. He actually has all his notes for a sequence of years as well, okay? And short versions of this as well. All right, so many references, and I have them there. Not that you will go and click them, but I want to be able to click them when I need them. Okay, it's for me. And if it is for you, then that would be fantastic as well. All right. So the idea of sequential Monte Carlo is to approximate sequential probability distributions. And the particular examples we will do, these sequences will be generated with time, all right? So we need to do it in a way that is efficient, so the problem doesn't become so complex as time moves on, right? So imagine you have a distribution that evolves with time. If every time you do it becomes more complex and more complex, then we're in trouble. But let me just say, and maybe in next week, I am going to show you that these methods, even though you will get the impression today that they're on for dynamical systems, actually, they're used extensively for problems that have 0 dynamics on them, for static problems, okay? So they're extremely powerful. You just need to play with them, but there is nothing necessarily dynamic in the way that these methods need to be used. But today I will sort of elaborate on the dynamical aspect. but the same equations again would be used for static problems. You can do anything you want with them, literally. You know, sampling high dimensions, compute eigenvalues here of operators, compute free energies, solve differential integral equations, do lots of things in physics and chemistry, like sample polymer chains. And I don't know if you will get that homework problem this year, but students in chemical engineering, where they want to compute unsampled properties of macromolecules, basically they use sequential Monte Carlo to sample. For some of you that may have seen there, if you're coming from different communities like in robotics, some names that go with sequential Monte Carlo is particle filtering, for example, or smoothing methods. So if you hear the word particle methods, really they are sort of subcases, if not the same thing as sequential Monte Carlo. All right, so what I'm going to do is we are going to go elementary today, all right? And I'm going to introduce the state space model. All right, so what we assume is we have a random variable, and these are realizations in time, x1, x2, xn. And so this is a chain of interest. And to define this chain, we need the following. We need to have some initial density that tells us how we sample x1. And then for this particular model, we need to have some dynamics, in essence, to describe how, if we know the state at time n-1, we sample the state at xn. And the dynamical model is defined through this density f. So remember, when you see f, is basically defining the dynamics from xn-1 to xn. Notice that this is a Markov chain because xn depends only on xn-1. Okay, and so that, you know, you can put here more history dependence. You can put xn-2, xn-3, etc. But what we discussed here, xn only depends on xn-1. So this the prior distribution of all the states. So let's see what the notation is. You notice this x is a bold x, so it's a vector, and includes all the states from 1 to n. All right, that's standard MATLAB notation. So it's the probability of all the states from 1 to n. So if you write it explicitly, that's what it is. And this is written as the probability of the state x1 times from this product from k equal to 1 of f of xk given xk minus 1. We agree? So this is the prior distribution of the states. Now, there's nothing fancy about this model, right? Because there are no observations or anything like that, but sort of we will use this as a skeleton to come up with more interesting dynamical problems. So let me give you a few examples from different fields on this. So let's say you're trying to track a missile on the plane. So the state here, x, is defined by the following variables. x1 and x2 are the x and y coordinates of the missile, and v1 and v2 are the velocities in the x and y directions. So at every given time, the state consists of the two locations and the two velocities. And this Markov model, basically, if we're going to try to put the dynamics on a Markov model, it looks like that. Okay? So notice this is a vector of 4 by 1. Okay? This matrix A here is 4 by 4. And we put some Gaussian noise. And actually, if you look, if you expand the vector xk and you expand the vector xk minus 1, this equation here makes lots of sense, right? It says the x coordinate at time k is what? Let's look at this equation. I see a matrix A there. So it is the x coordinate at time k minus 1 plus t, so you can think of t being like a time step, times the velocity at the previous time step. You see that? This sounds like an explicit integration scheme the way that I have written it. It doesn't have to come from any integration scheme, right? But basically, this is what's called a constant velocity model, and you can write it in a compact notation like that. And again, the details on the noise looking like this, it's not important for this course. So the dynamical model, the probability of xk given xk minus 1 is a Gaussian with a mean alpha xk minus 1 and a covariance sigma that is defined by this matrix. All right, another very popular model in machine learning. So, you know, one of the things that you should never do, because it's very rude, when somebody is very slow to complete a sentence, you go and complete the sentence for them, right? So here, in speech signals, for example, you can think if you have some previous words, and effectively what you can go is figure out what the next word is, and you do this with an autoregressive model. So if you have these speech signals from k minus 1 to k minus d, you can see what the next signal is going to be, all right? So this fits nicely on our Markovian model, and then you put some Gaussian noise. So if you put the signals, if you define the vector uk to be sk to sk minus d, you can actually write that uk is a times uk minus 1 plus a matrix b, b is a vector here, actually times this noise vk, all right? And you can actually see that this equation here makes sense because uk, the first element that involves is sk, and sk is this coefficients times uk, you know, sk minus 1, sk minus 2, sk minus d. Can you see this? The first row, right? The first element of uk is going to be sk. The first element of uk minus 1 is going to be sk minus 1, sk minus 2. And the other elements, like for example, in uk is going to be sk minus 1. So that's why you have here 1, because sk minus 1 is going to be equal to sk minus 1 from there. Okay? So anyways, it's a little bit fancy to write the transition, the dynamics for this model. So you notice the way we have written this equation, right? Effectively, there is a Gaussian that defines the first element of uk, right? This times that plus the noise is a Gaussian. And then for all the other states, because, you know, sk minus 1 on one side is going to remain sk minus 1 from the other side, so no information. So effectively, the states of uk minus 1 from 1 to d minus 1 are the same as the states of uk from 2 to d. You don't update those. At each time, right, you update the next signal, the other d minus 1 components, you keep them the same. So you put this delta function to write this in this manner. Okay? So again, the idea here is you have a transition model, a dynamical model that tells you how to go from the state at k minus 1 to the state at step k. Now, these coefficients here that you see, you can actually introduce dynamics on these coefficients as well. There's no reason why these coefficients will remain constant. So what actually you can do is, you can even define an autoregressive model for the coefficients themselves, okay? So effectively, you can define that the probability of alpha k given alpha k minus 1, it's another Gaussian, all right? So if you do this, effectively, you will need to extend the previous model, not only to include uk, but also to include these coefficients alpha k in the model. And there's a trivial way of doing this by actually enhancing the state x to include both u and alpha. And when you do that, the dynamics are basically defined exactly as before, which is the last two terms, plus a Gaussian that defines the transition of alpha k from alpha k minus 1. So it's a little bit more complex model that allows you to, you know, to put some dynamics on the coefficients as well. I mean, there's no reason if you have a model and this dynamics, why should this model remain the same thing in time? So here what you do is you evolve this with some Gaussian model, and the rest remains exactly as we had before. Bottom line is, all right, for all of these problems, they fit in this category, okay? You start from some probability distribution, that's your initial state, and then given xn minus 1, you have a probability to actually sample what xn is going to be. And there's only dependence on xn minus 1, so the prior model looks the way that you see it here. Again, this is a very powerful model. It's applied everywhere, from biology to ecology to robotics to navigation to whatever problem you tell me. I can make things sort of to look like this Markov chain. All right. Actually, all of these things are also applied in econometrics. So even if you want to find out how stocks evolve with time, so you can play the stock market, the same type of equations. So since you're not interested to make any money in your graduate students, I'm going to bypass that. Okay, so let's make this model a little bit more realistic. So there were no observations on what we had before. So we only had the state x. So now what I'm going to do is I am going to introduce these observations y, all right? So what I want you to think is, so you have this state x that evolves, but somehow you cannot observe it, all right? You cannot access it. What you can observe is maybe some noisy versions of the state, okay? So you can think for now that y represents some noisy version of the state, okay? So the state evolves, all right? So the dependence is the prior model is exactly as we had before, but now I call these states hidden variables because we don't really observe them, right? We don't know what they are, okay? These are hidden variables. What we observe is y1, y2, yn, and the way that I denote this with arrows here imply that y1 really depends only on x1, y2 depends only on x2, etc. All right? So, you know, if you wanted to compute y2, you can do this if you know what x2 is, and that's the only information you need. But of course, you know, this state is unknown, so the real type of problems that we would be interested to handle today and tomorrow and maybe on Monday would be if somehow I give you these y values, your problem will be to go and compute the states x1 to xn. Okay, that's the problem would be of interest. All right, so how do we settle mathematically this problem? First, the prior model looks exactly as before. So we sample x1 from some distribution mu. We have a dynamical model, all right, for the hidden states, exactly the same as before. But now we also have an observation equation, okay? So, and the observation model is defined by this distribution G, and it says, if I knew what the state is at time n, then yn is sampled basically from this distribution G. All right, so you can appreciate that this is the G model. So if I knew x1, y1 is a sample from G that is defined using the value of x1. Okay, so this is the observation model. This is the state transition model, or the state equation, or the dynamics, if you like. And because the way, when I write this like that, right, you notice yn depends only on xn. So if I tell you that I want the probability of all the observables given all the states, conditionally all these y's are independent random variables, so I can write this probability as the product of all the g's the way that you see here. Okay? So you can think actually that this is the likelihood model, all right? And all of these things up there is the prior model. I'm sorry, this is the prior model, and this is the likelihood model, okay? So in essence, multiply them together, you can get the posterior of x, and there you can compute, given the observations, you can compute the posterior of the x's, or maybe point estimates if that's of interest. So the problem is to recover the values of xn for n greater than equal to 1 if we know the observations yn. And again, why? So we care about this problem because it comes all the time, right? But you can appreciate the fact that if we're going to do, if we're going to compute the posterior, equation you need to have is the following. Can I keep doing this forever? In other words, can I actually go and compute the posterior as n increases to infinity? And even so, or let me put it as follows. When you compute, let's say, the posterior for n equal to 2, is the posterior for n equal to 3 going to have the same cost of calculation as for n equal to 2? Or the posterior for n equal to 1,000 going to have the same cost as the posterior for n equal to 3? And obviously you appreciate that when I say for n equal to 1,000, that will involve x1, x2, x3. You have to resample all of these things up to x to 1,000. So what really we need to do, right, that's what our objective will be, is somehow, let's say if we do the calculations up to n minus 1, and we have samples from the posterior of x1 to xn minus 1, the idea will be to find a smart way to reuse the samples rather than recompute the things from scratch. So somehow being able to update them in a way that there will be samples from the joint distribution, the posterior of x1 to xn. All right? We want basically to be sure that the cost of computing the posterior of these variables does not increase exponentially with n, right? We want to keep track that somehow the cost, it is the same if possible for each n. Okay? That's the objective. So let me give you some, so this is called the state space model. So I am going to give you some examples. So the easiest example is a linear Gaussian model. So if some of you have taken control theory or something like that, this is something you will see there all the time. So the transition model looks like that. The noise is Gaussian, but the observation model is also linear. So this constant, these matrices that I have here are constant, and the noise is also Gaussian. Okay? I can tell you that there is an analytical solution to this problem. So if I give you the observations y and I tell you go and compute what is the posterior of x, or any other equation regarding x, there is an analytical solution to this problem, and it goes under what name? What is the name that involves this this analytical solution? What's the name? For a linear Gaussian state space model. Do we have any electrical engineers? No. Do we have anybody who works? Kalman filter. Thank you. That's the Kalman filter. Okay. So usually if we had 50 of these courses, right, I will go and derive these equations so that you see them. But you don't really need to do them because we want to do things beyond the linear Gaussian state space model. We won't be able to handle this even if these matrices, let's say, are completely functions of the state, so this is a nonlinear model. So let me give you another example, and this example is extremely popular to test sequential Monte Carlo codes, and it's called the stochastic volatility model. This comes basically from econometrics, and the state x1 is a sample from a Gaussian, where this parameter alpha is less than 1 in absolute value. The transition model is very simple, right? So this is scalars. The transition model is very simple. The only complexity, and this is why this is a very nice model to test, is that the likelihood model involves a nonlinearity. You notice that the observations is an exponential of the state. So immediately that messes things up, and it will require some sophistication to be able to handle it. So if you want this in a probabilistic fashion, this is the state equation, right? Simple Gaussian, and the observation model is zero mean, and the variance basically, if you square this thing, will be beta squared times the exponential of xn. Okay, so this is now you can appreciate, right, that if you don't do things right, you can see this variance exploding with time. All right, it's exponential of xn. So you need to actually do this calculation correctly. So this actually model it is used in every paper, every quarter to test. If you're going to propose some new sequential Monte Carlo algorithm, you basically have to do this problem. It's a standard, and it's actually not very difficult to do. Let me give you another, since we discussed about the tracking problem where we had you know, the coordinates in x and y, and then we had the velocities in x and y. So we can actually make that model to look nonlinear. And the way we do this is as follows. So we're going to define y, all right? We're going to define y to be the angle. So, you know, imagine you have x and y coordinate system, right? And you have a missile somewhere. You want to know what is the angle from the horizontal direction that the missile is. So effectively, the angle is the inverse tangent of the y coordinate divided by the x coordinate. So if you do like this, the observation model basically with some noise involves, you know, this mean value. It's a nonlinear function of the state. So this problem becomes, again, a nonlinear problem that requires special attention to do it right. So the dynamics, you can keep them exactly as we discussed in an earlier slide. You know, you can have linear dynamics, but the observation model, the likelihood here is nonlinear. So in robotics, for example, this is, you know, standard. Actually, there are lots of books now in out there on probabilistic robotics, and maybe half of those books is around this type of techniques. Okay, so let me go back to the state space model. Let me see if I need to, you know, I'm going to try not to jump slides today because they are sort of very basic. So, so I remind you, this is the state, all right, the Markov chain with the dynamics, you know, of x2 depending on x1, of xn depending on xn minus 1. And these are the observations, and we have an observation model, so the yn depends only on xn. So we're interested to compute the posterior of the state. So the posterior of the state at time 1 looks like this. This is what we want to compute, the probability of x1 given y1. At time 2, we're interested on the probability of x1 to 2 given y1 to 2. So really here what x1 to 2 means is the probability of x1, x2. I have two variables, right? And similarly, when you reach time n, you're interested in the probability of x1 to n, which is x1, x2, xn, okay? And again, just to motivate you why we do this is, you know, obviously we're going to do this sequentially, we collect data, but can somehow use, let's say, if you take samples, you manage to take samples from this, can you reuse them to actually do the update and compute this probability? And then can you use these samples to compute the next probability? So that would be our objective. So the prior looks like in the Markov chain model we had before, the prior for, you know, the probability for the initial state, and then these transition probabilities. So this is the prior of the states from 1 to n, and the likelihood is nothing else but the product of this observation models of yi given xi from y1 to n. All right. So we want to compute. This is the posterior we want to compute. So if I use Bayes' rule, in essence, the anormalized posterior is the joint probability of x1 to n and y1 to n, right? So we don't really care about the denominator here at this point yet, right? So if we somehow can get samples from this normalized, posterior, that would be great. And we can rewrite this normalized posterior as the product of the prior of the states times the likelihood, the probability of the observations given the states, and I'm writing this explicitly like that. So our distribution really, in an unnormalized way, it looks like this, and I want you to visually try to remember it, because you will see equations that may look very complex. So I want you to look at this and say, yeah, right? So what is again F? What are these terms? What is this term here? What did we say F is? You can see here, I mean, you don't have to remember even names, right? You can see, so what is this terms here? What train?
Markov.
The Markov chain. So that's the dynamics of the model, the evolution of the state, right? So this is the transition, the model for our states, and this is the observation model, okay? So the initial state, the transition model, and this is the observation models. So really this is the prior, right, of all the states without any observations. This is the likelihood. Together they get you the normalized posterior. And the denominator, so if you have this, right, if you integrate this with respect to all the states, you really get the normalization factor P of y from 1 to n. And this normalization factor is very important because I remind you, the likelihood of the data is what you need to, when you want to do model selection, when you want to compute parameters, the objective is always, how do you do it? You do it by maximizing the marginal likelihood, and the marginal likelihood is this complicated integral. So when n is very large, that gets very complicated, okay? But taking samples from the posterior, you don't really need this term, all right? But there is many important problems in engineering and physics where this term is essential. For everything else, somehow if you want only to take samples, this unnormalized posterior, again, this is the unnormalized posterior, this is the joint, if you like, is sufficient for us to work with. All right, so let me put some notation. So we are going to write this is the posterior, so this is the notation, we're going to use this for the posterior of the states from 1 to n, okay? And I'm going to write this, so pi, the definition is this term here, all right? So we don't need to carry explicitly all the observations y from 1 to n. So this is the posterior of all the states given the data up to time n. And I write this as the unnormalized posterior that I denote here as gamma, divided by the normalization factor. So the normalization factor is the probability of the data that I had on the previous slide, and the unnormalized term in the posterior is again the joint. There's nothing different from the previous slide. The only difference is I have introduced, I called this unnormalized posterior gamma, all right? I have called this gamma, and I call the target posterior time n as Pn. And notice there is an index n everywhere, right? Because we're going to have to do this sequential in time, right? We're going to have to go from one time to another. That's one thing. And you maybe haven't thought about this, right? This sequence of distributions has the number of variables on each of them changes. It's not the same. So when you start with P1, it has only one variable, x1. When you go to time 2, it has x1 and x2. When you go to time 3, x1, x2, and x3. So we don't really know how to handle this. It's not like you have a distribution of a fixed dimension that you work with. This is a distribution that has dimensionality that increases with time. So obviously how you do this is tricky. Again, I don't want at this point to throw sort of other ideas, but we will see that even if the dimension was fixed, okay, what we're discussing now can actually be applied to those cases as well. But we will first, let's do and understand this dynamical problem, then we will see what else we can do. So if, let's say, somehow you can compute this posterior or take samples, you may be interested to find, let's say, point estimates. You may want to find the map estimate of this posterior, okay? Or you know what, you may say, I don't really want, you know, I have observations up to time n, but I'm only really interested to find state xk. So you know, you do experiments from now to, let's say, n equals 100, and you say, I only want to know the map estimate for this marginal posterior. So you only are interested on the values of xk, k less than n. You don't interested to compute all the state. So in this case, you can see this marginal is basically, you have integrated out all the x's except k. All right, so you integrate out from 1 to k minus 1 and from k plus 1 to n. In other situations, if you have this distribution, maybe what you're interested is to find the posterior mean. And that requires to be able to do this integral. And if you are thinking of Monte Carlo to do this integral, you need to be able to take samples from this. So you have observations up to time n, and you need to sort of be able to take samples from the posterior of xk given y1 to n. And notice here, right, k is less than n. So in essence, this posterior is defined using data not only up to time k, but future data as well. And you say, wait a second, but how is it possible that the future affects what's happening now? Well, if you think about it, what is happening now is going to affect the future. So knowing something about the future is going to actually smooth the calculation of xk. And that's why this is called a smoothing problem. I mean, if I know, if I know what happens now, that defines the future, right? So if I know the future, we'll have something to say from where I came, and so this is what the type of calculations that are being involved in that marginal posterior distribution. Let me see if we're going to do this, if this is an important problem. So there's lots of problems in physics and chemistry, statistical mechanics, everywhere. So let me give you an example where somehow the marginal likelihood is actually what you need, okay? Not the posterior. So imagine that you have this particle xn, I call them a particle, right? It's a random variable that evolves with time. And I sample x1 from some initial distribution. This is my transition model, exactly as before, okay? And, let's say that we're interested on the probability of something, of some failure, or in this case, I call this the probability of the particle being killed. All right, some rare events, right? So you can you can interpret this in any ways you want it. But let's define at each time n the probability of the particle to be killed to be 1 minus g of xn. Okay. So for now, interpret g of xn as basically the probability of not being killed at time n. It has nothing to do with the observation model that I discussed before, all right? So I call this, the probability of not to be killed at time n is 1 minus g of xn. Okay, so here is the problem we want to do is, let's take a time capital T, and we want to, capital T is the time at which the particle is killed, and we want to compute the probability that capital T is greater than n. All right? So again, t is the time that the particle is killing. We want the probability of capital T being greater than n. So up to time n, according to this definition of the problem, has the particle been killed or not? No, because this probability says, find me the probability that capital T is greater than n. So up to time n, the particle has survived. So you can think of this as you know, as such, you know, you can say this is equivalent to a particle basically surviving up to time n. So let's compute that. Let's compute the probability that the particle survives at time 1. Would you agree with me that that probability is equal to that? If we knew the state x1. If we knew the state x1. So if we knew the state x1, right, two things need to happen. This is the probability that we sample the state, and g of x1 is that it survives at time 1. Okay? Now, obviously, when I say if I knew the x1, I don't really know x1. So we have to marginalize on x1. So really, the probability that the particle survives at time 1 is this integral. You see that? Again, if we knew x1, means first we have to sample it, and then the particle has to survive. And because we don't know x1, we need to average for all possible values of x1. You remember the probability rate of survival at time 1 is the expectation of given x1 that the particle survives. All right? So we do have to take expectation with respect to x1, and that's this integral. I mean, you're not going to give me an answer that depends on x1 because x1 is random. All right, can somebody tell me what's the probability that this particle will survive at time 2? So what's the probability that this particle will survive at time 2? Using, you know, the notation that we have up there. So the first thing, if the particle is going to survive at time 2, means it has survived at time 1. Right? So let's start, okay, it survived at time 1, which means we have all of the things you see already there. And now it has to survive at time 2. So to survive at time 2, what, given the state x2, what it needs to happen? First, I need to select x2 given x1. That's my transition model. And then, given x2, the particle has to survive, and that probability of survival is g of x2. And then I have to average on x1 and x2. So what's the answer? Why there's so many words? I wanted just the answer only. Okay, so basically, this, given the state, this is the probability that it survives at time 2, and given the states, so we have to basically average these things with respect to x1 and x2, take an integral of this with respect to x1 and x2. Okay? So let me give you the final result up to time n. All right? So up to time n, the probability basically that the time of failure will be greater than little n means that it has survived up to time n, which is the expectation with respect of all the states that, given the states, the particle has survived. And this is this product that you see here. That first you select x1, then you transition to all of the states, and then it survives in every state. And then you average, you integrate basically all the states out. And you look at this integral, and what does it remind you? What is that integral that we had before on the general framework for the state space models?
Evidence.
The evidence, that's basically the marginal likelihood. It's the probability of y 1 to n. So there is, why computing failure probabilities actually is a very difficult thing to do in statistics, because it's related with the marginal likelihood, which is one of the most expensive type of calculations, right? But in all engineering problems, everywhere in science, nobody cares about something that happens all the time. You're really interested to know for things that happen once in a million times, and so this requires this high dimensional integration. And obviously you can appreciate as n increases, this becomes very high dimensional integral. However, for the Markov model, I am going to show you actually that this integral, you can do it recursively with a very low dimensional integrations. Right? I'm just giving you the very general answer, I mean, the setting now if you like, but the good news would be for the hidden Markov, for the state space model, you will be able to do this not with a horrendous cost that this equation, this integral implies. So we will be able to actually do this precisely with much less computation. Okay, and I want to tell you this even though I will not use those formulas for Monte Carlo analysis. All right. So that's basically the setting. As I said, this is the normalized distribution. So effectively, the normalization factor here is actually the probability that the particle has survived at the time n. All right. So what's going to follow now is going to look a little bit complicated, this type of calculations, you learn them when you take a course that's on Kalman filters. You learn this when you take a course on probabilistic graphical models where the derivations are a little bit easier. I offered a course like that last semester and maybe next year. But today I want to sort of derive these equations from a trivial sense. So the derivations may look sort of a little bit complicated, but actually if you put an effort and you learn the machinery of how these conditional independence relations that I use are coming in a graphical way, not with equations, you can derive practically everything in a few lines. Actually, no derivation that I'm going to give you today takes more than 2 pages, each of them. So it's basically, it's not complicated, but I think the derivations can be completely avoided if you do this graphically, okay? But we will not discuss that because it takes some extra knowledge. All right, does this look complicated already? All right, so let's return to the problem at hand. We want basically to be able to compute this posterior of x 1 to n given the data y 1 to n. And what I want to do is I want to start building some recursive equations where somehow if I compute this posterior at n minus 1, I should somehow be able to reuse that at time n. That's the objective, right? I mean, this posterior here we're going to compute at time 1, at time 2, at time 3. So can we actually write down some recursive equations where I can use this posterior of p of x 1 to n minus 1 given y 1 to n minus 1. Can I reuse this to compute that? Okay. So let's see how these recursive equations are going to come. And I'm going to give you many of those because depending on what you want to do, they have different accuracy, different meaning. So I'm going to give you first the standard one with elementary use of Bayes' rule. Really nothing. So let me do this approximation. No approximation, it's exact, okay? So will you agree with me that this is what we want? And it's really the same as this red thing on the top. You agree that this is the same as that? From Bayes' rule? Yes? It's the product rule, right? So this is the same as that. So what is the blue thing? Look at the blue thing and will you agree with me that the blue thing cancels out? Do you agree in other ways that this is equal to that? I mean, I can write this, right? P of this x given that y times P of y, which is that, so they will cancel, and this will cancel with that. Yes? All right. So let me do the following thing. I'm going to take this red term, I'm going to put it there. So it's the joint distribution up to time n. This is the joint distribution, which is nice, up to time n minus 1. And then I have the marginal from y from 1 to n minus 1 divided by the marginal of y from 1 to n times this probability of x from 1 to n minus 1, okay, given y of 1 to n minus 1. Now, you remember the expression for the joint distribution? Remember, the joint distribution is the unnormalized posterior. What is how do you compute the joint distribution for our state space model? It was the product of many terms, right? Prior times likelihood. It was the mu term first from the initial state, and then the product of all the f terms for the evolution of the state, and then the product of all the g terms. If you expand this thing in the numerator and you expand these things in the denominator, the only difference in that product expansion is really the evolution, is the term that gives the probability of xn given xn minus 1 on the top, and then the observation of yn given xn. Everything else cancels out. Yes? All right? Where do I get now this term? Look at this ratio and tell me, is this the same as that? Again, product rule. Can you write this probability of y1 to n as the probability of yn, comma, y1 to n minus 1? And then write this as the probability of yn given y1 to n minus 1 times the probability of yn minus 1 to n minus 1. So this and the other term will cancel, and the only thing you will get is that. Product rule. The ratio of those two terms, right? This involves variable y1 to yn minus 1. This involves variable y1 to yn. So separate yn and then write the product rule for the denominator. You will get this term times this term on the numerator, and they will cancel. And then effectively what you get, if I write this, you get this nice formula on the right-hand side. And the first thing I want you to observe is the following. We want to compute the posterior of x1 to n given y1 to n. And immediately you can see here, it already involves the same posterior at the previous time. Which is nice, because that's what we wanted, right? We wanted, if we knew the previous posterior, to be able to update to compute that posterior. And in the numerator, actually the calculations are trivial. It's one observation model at time n, one evolution plus the previous distribution. Nice. The only problem up to now, right, that it doesn't look very nice, is the term in the denominator. And unless we can update the term in the denominator, iteratively with time, this formula is not going to be very useful. Okay? So the numerator looks very nice. The previous posterior times these two terms, together, we can compute them easily, but then there's the denominator. So let's work on the denominator in two lines. So the denominator here, it says the probability of yn given y1 to n minus 1. So what I do is I plug in xn and I integrate xn out. That's what rule of probability? The sum rule. Okay, so I just plug in xn there. So then I use actually the product rule of probability, and what I do is I write this as the conditional of yn given xn and this term here times the probability of xn given that. And you notice on the first term, it's the probability of yn given xn and all the previous y's. and I don't show those previous y's. Why is that? Because yn only depends on xn. Yn only depends on xn, right? So there's not going to be dependence on this previous data. Xn defines yn. So effectively what I have is this observation model times p of xn given yn to n minus 1. And this, again, looks a little bit weird, because if you think about it, all right, this term really what it is like, if I know all the data up to n minus 1, you say, predict me what the next value is going to be. So really it's a one step ahead prediction. If I know all the data up to n minus 1, tell me what xn is. So the way you do this, again, very simple. You write, you plug in an xn minus 1 there, and you integrate xn minus 1 out simultaneously with xn. So here there was integration on xn, and because we plug in an xn minus 1, we're going to integrate, it says here n minus 1 to n, so it's really an n minus 1 and n. And then I use again the product rule of probability, and I write this as the probability of xn given xn minus 1 and all of this. And of course xn only depends on xn minus 1. And then what you have is the probability of xn minus 1 given y1 n minus 1. Okay? And do we know this term here recursively? This is the probability of xn minus 1 given the data up to n minus 1. So recursively, remember, recursively, this is what we work on. So recursively, are we going to know what the probability of xn minus 1 is given yn minus 1? So we obviously, we already have the posterior at time n minus 1, and what this is just the marginal of that posterior. Final answers. The calculation, basically, to be able to update this sequentially involves two types of calculations. One that we call a prediction step, and one that we call an update step. So the prediction step basically involves, given the data up to time n minus 1, you try to predict basically the observations one step ahead, so from 1 to n, and effectively it's this term that you see here. It's f of xn given xn minus 1 times the previous posterior. So really this term here, you do this prediction, use only the previous data, and figure out what the next value of what xn is going to be at the next step. And then the update basically will be based on this formula, will be taking this, all right, this prediction times g divided by this term. And as I showed you, this term actually can be calculated again recursively, right? But the good news is, if the only thing you need is the normalized posterior, you don't really care about the denominator, and the only thing you care is the numerator, this normalized posterior, which is the previous posterior. I'm sorry, this is the predictive, the one step ahead distribution times the observation model. I mean, think about it, that this is how simple it has become, right? If you want to compute the posterior up to time n, effectively what you do is you do prediction one step ahead using the previous posterior, all right? And then using this predictive distribution, you multiply it by the observation model of time n, and you're done. And there are no approximations here, this is exact. All right? These equations are all exact for any model. Doesn't have to be Gaussian or anything like that, right? Obviously, it needs to fit on our state space model, which means we need to have a Markovian dynamic, so the xn depends only on xn minus 1, and again, the observations yn depend only on xn, and there is thousands of problems, basically, that fit in, millions of problems that fit in this category. So really what I want you to do is, right, the derivations are exercises in the product and sum rules, but these are the two nice equations. I want you to think that really this is your objective and you want to do it iteratively, and iteratively means you know the distribution at the previous time. So the first thing you do is do one thing, a prediction of xn, one step ahead, The only thing you really need to do to this is multiply with the transition model. And then you say now, if I want, given all my data, right, to update x1 to n, the only thing you have to do is this predicted distribution, you multiply with the observation model at yn, at time n, and that's it. Okay? So these two equations are actually the most popular recursive equations in state space models. Now, notice that when you apply this algorithm, in what direction do you apply? You apply it forward, right? You're moving in time from time 1 to time 2 to time 3, etc. Okay? This is very important because now I'm going to try to confuse you. I'm going to give you some algorithms where actually you do some things forward, some things backwards. Okay? So in this algorithm, you predict one step ahead, and then you correct it with the observation model to include yn, and that's it, but it's a forward calculation. You are going basically from the calculation you had at n minus 1 to the calculation at time n. So in the way that we have it here, right, we basically are going to compute the posterior of x1 to n given y1 to n. And let's say that you don't really care about all the x's, and the only thing you want is to update the state xn. Okay, you only need the marginal. I mean, I will show you with Monte Carlo methods actually that the next slide is not really very helpful, because if you know this distribution in terms of samples, the marginal of xn is directly there. You don't have to do any calculations. But let me just summarize the equations. The only thing you care is this distribution, right? So you don't really care all of the x's, but only you want to update the state at that time. So this distribution, so you know the names, okay, it's a marginal posterior, but in the literature, it's called the filtering distribution. Okay, it's very important to remember the name. So filtering means you basically compute the state given all the data up to time n. Okay, and so the calculations basically are identical to what I had in the previous slide, right? So let me just give you the two steps here. So the first step you will do is, given the data up to n minus 1, you will predict the state xn one step ahead, and this involves this integral that you see here. Okay, so what you do is you take the posterior of xn minus 1, all right, and then you multiply with the transition model, and you average over all states xn minus 1. I mean, effectively, that's the product and some rule of probability, but it's a recursive forward formula. Use the previous value, multiply with the transition model, and get rid of xn minus 1. And then the update formula for to compute the posterior of xn is nothing else but taking this predictive distribution and multiply with the observation model exactly as before. And the denominator here is slightly different from before because of the way that the marginalization has worked. And the only thing I'm going to say, it's actually this, you can show it's basically it doesn't take any calculations. You can show that predicting what your next observation will be, if you know the observations up to n minus 1, it involves recursively again. This is the previous filtering distribution times the transition model times the observation model, and you integrate the states xn minus 1 out. What is nice, and maybe this is worth to see on this slide, is that this marginal that comes out when you're interested on this marginal posterior, it only involves two-dimensional integrations, only two variables. So if you want to compute this fully, including the normalization factor, you notice the integrals here are in two variables. Very nice. You remember before we had variables from 1 to n, you had to compute this. You can see here, this integral involves only variables. You integrate n minus 1 and n, okay? Again, these calculations are used to compute the filtering distribution. And just remember conceptually, right, the equations are not very important. So the first thing you do is you assume you know this distribution at time n minus 1. So then you say, what's the probability of the next state at time n? And so this is the prediction. And then you say, well, how do I update the prediction if I now collect data yn? And effectively, you have to multiply with the observation model that you see here. And the rest is just some intermediate formulas that you need to use. All right. So let me, since I mentioned how somehow we got rid of this high-dimensional integration to compute the marginal of the data, so let me give you a very general formula that shows you how powerful these methods are. Okay? So this is the marginal likelihood, right? This is the evidence. Do you agree with me that the product rule of probability gives you this generic formula? Right? The probability of y1 to n is the probability of y1, the probability of y2 given y1, the probability of y3 given y1 and y2, etc. Okay? So the probability of y1 to n is this generic formula. But as generic as it looks, all right, as generic as it looks, somehow, in computing the marginal posterior, this is what we needed, okay? All right, you can see here, all right, this is what we needed, and it comes out that this, so this is the proof of the equation I had on the previous slide, that this involves only two-dimensional integrations. So, let me, now my brain went to the right place, right? So this is what we used before, but if I return back to this equation here, you notice this equation involves the marginals of yk given all the previous observations. So those distributions look like this, and even though they're high dimensional, they depend on all of the previous y's. You notice all of these distributions, they only require integrals in two variables, okay? So to calculate the marginal, basically, you don't have to integrate all the states out. You can do it with all these products where each of the terms involves integration into variables. Really nice. Which means, you know what? To calculate this probability at n equal to 5 or n equal to 1,000, it doesn't take more cost. It's always two-dimensional integrals. Right? Always two-dimensional integrals. All right. Let me see if I can do something very different now. Another recursion that is going to look very, very weird to you. So I remind you that the previous regressions, recursions, they were all forward, right? From n minus 1, we go to time n. So let me define, so remind me, what's the filtering distribution? What did we call filtering? The marginal of xn given what? To n. So basically it's like at each time having all the data, all the observations, what's the state xn, okay? Now, let me define a new distribution that is very important, and it's called smoothing, because it's going to be more smooth actually when you compute it, where you compute the marginal of xk given all the data before k and after k. All right, this is very important, okay? So this is the marginal of xk given all the data up to time n. So you obviously this you cannot do it online, right? So the idea here is if you collect all the data, what's the best you can say about xk? So that distribution is called the smoothing distribution. All right, so if you finish, you observe everything, then you can come back and say, now can you tell me what xk is? So obviously this will give you a more smooth distribution than the one that that you only use data up to time k. So let me, because it's 140, okay, so let me just tell you how the algorithm is going to work, right? And again, product and some rule of probability, nothing else, okay? 2 steps. One step is I'm going to do a forward pass, and you remember when I go forward, can I actually, what distribution is this at its time k? How do we call this again? How? What distribution is this? What's the name we gave to it again? Filtering. All right? And what name do we give to this distribution? Here we have data up to k, and we predict the value is the predictive distribution. Right? It's the predictive distribution, one step ahead. Okay? So these calculations, the filtering and the predictive distribution, you start at time n, 1, you go to 2, to 3, to 4. So recursively, moving forward, you can compute all of these distributions for k1 to n. So now, the objective is to compute the smoothing distribution, the probability of xk given y1 to n, where n is greater than k. So I'm going to give you the formula, all right? And the derivation is one line, all right? You guys, you should read it. So let me see what the formula, the way it looks like. It says backward step. So we have gone up to the step n, and now we're going to start going backwards. n minus 1, n minus 2 until we go to n, to compute the probability of xk given y1 to n. So what does this involve? This is our objective. You notice it says you need to know the smoothing distribution at what time? At k plus 1. So actually when you're going to start this backward recursion, what is the value of this? What distribution this is going to be? It's going to be really the probability of xn given y1 to n. I mean at the end. All right? So you notice here k plus 1, that's the smoothing distribution there, it's k. So I'm going backwards. And the rest of the terms, basically, what do they involve? The transition model, right? Nothing fancy. What is this? This is the filtering distribution. And what is that? The predictive distribution. So you go forward, you save the filtering distributions, you save in the computer the predictive distributions, and then you start going backwards after you finish. After you have been all the way to time n, you go backwards starting from n, and this backwards recursion will give you the smoothing distribution of xk given data y1 to n. So this obviously will provide much smoother results than the filtering distribution of xk, where you only use data from 1 to k. Again, the derivation is really, it's nothing, but the calculations basically lead to these 2 steps, so you can really program this efficiently. Now, you may say, am I going to tell you how you program this? Because these are integrals. Well, if all of these distributions tend to be Gaussians, like in Kalman filtering, all of these calculations, you know them analytically, okay? So I'm not going to tell you what they are. So the forward recursions and the backward recursions, you know, you can do them analytically. The idea here is to actually use Monte Carlo approximations, and in particular sequential Monte Carlo that I will be discussing when we finish with this to do this type of calculations. All right, and so this there is a note here, you know, that somehow you have to pay attention when you do this smoothing things, because this distribution that you get on the denominator basically can blow up. Okay, so there is, you know, so that just you need to pay attention to these things. Okay. Now, let me just, because it's 1:44, let me just use your imagination here. If you take more advanced courses on probabilistic graphical models, this type of update formulas, you'll be able to interpret them in the context of what is called messages. So basically, every time you do forward calculations, it's like passing messages from node 1 to node 2 to node 2 to node 3, etc. And then the same thing when you go backwards. And it comes out that all these calculations can be interpreted in terms of the messages that arrive on the node from the left and the right. So actually, you will learn later on, you don't have to memorize any formulas because you draw this in a little picture and you say this margin distribution is the product of this message and that message. And what those messages are, they're literally these distributions that you see on these slides. All right, so I'm going to try to start tomorrow using these recursions to basically extend the ideas of importance sampling and give you some preliminary methodologies for extensions of importance sampling to sequential importance sampling. So we'll continue tomorrow for the lecture. Thank you.